We appreciate you being here. This is going to be Plasma 101, but we have a very special treat for you. My name is Rick Lee. I'm a chief operator on the D3D tokamak, and I have my professional partner here, Alex Nagy. He's a engineering manager from Princeton Plasma Physics Laboratory on long-term loan to General Atomics. So there he is right there. Okay, so we appreciate you coming to this Division of Plasma Physics workshop, and it has allowed us to do something that we've never done before. And so you will be the inaugural team that takes a virtual tour of our D3D tokamak. We operate the largest magnetic confinement device for fusion research in the country. And it's really our great pleasure to expose you to that. Yes, we'll talk about plasma, and yes, we'll talk about fusion, of course, and yes, we'll show you some things that you can do in the classroom. I presume you all got your plasma balls, you got your half-coated tube, and a few other things. We will show you a little bit later how we can understand how that plasma ball is working and what to do with that half-coated tube to try to get your kids interested in plasma, just the fundamental concepts of plasma. But the plasma that we work with here is a very high temperature plasma, and we use it for our nuclear fusion research. And in our nuclear fusion research, we have a machine that has vacuum, electromagnets, and lots of other things. So first of all, let me just show you how simple it is to make a plasma. Now, plasmas are simply ionized gas, and you probably know that already. So even when you take your clothes out of the dryer on a dry day, you can have some static going on there and have little sparks. Even those little sparks are a tiny bit of plasma. Not a whole lot, and it doesn't last very long, but that's what it is. So I have a handheld Tesla coil here that has high voltage, the 110 volts going up the cord, puts out about 30,000 volts over here. So it's a much higher energy per charge on this end. And we can break down air very easily with this. So let me just show you. I've switched it on. You can't see anything here, but I can go ahead and hold it up here. And you can see this nice little arc right here. So that looks like lightning. That looks like lightning. So certainly, I'm sure in the Memphis area, there's plenty of lightning at times. So there is a definite connection to plasma. Now, we also have some simple glass tubes. Now, this is similar to your half-coated fluorescent tube. And we'll talk about that a little bit later. But this has some gas in it. It has some argon in it. And if I can excite it, and you may not be able to see it, it's lightly blue. And if I ionize it, it becomes much brighter. Much brighter. So that's the plasma in there right now. Excited gas, excited, and ionized gas. So that's a very simple little plasma demonstration. You can do that with your plasma ball and your half-coated tube. You'll get excited gas in there. It may or may not be much plasma, but you'll get excited gas in there. We'll show you how to do that in a little bit. So let's talk about this. This is a fantastic opportunity to show you the state of the art of not only plasma science for fusion energy, but our actual fusion machine out there, inside of which we make 100 million degree plasma, 100 million degrees, of the order 10 times the temperature of the center of the sun. Pretty awesome, pretty awesome. Now, how do we hold on to that plasma? Well, nature has given us, 3 ways of doing it, but only 2 are practical for us. The sun and stars hold on to plasma using gravity. And we don't have anything on Earth here large enough, with enough mass, to produce that much gravity. So we can't use gravity to hold on to a plasma. But the other 2 knobs that nature has given us are electric fields and magnetic fields. And boy, do we use those. We use those a lot here, electric and magnetic fields. Now, you've probably, as high school teachers, you certainly have run a current, I hope you have, current through a wire. And if one does that, you get a magnetic field that goes around this way, right? It goes around there. If we bend that wire into a coil and we run current through it, then we produce a very strong magnetic field inside of here. And so our machine is made up of lots of coils, not with this little wire though, with much larger wire. And they are orthogonal. That is, some of them are in this position, some of them are 90 degrees to that. And so we have lots of coils on this machine that runs lots of current. I mean, hundreds of thousands of amps of current through the coils. And so behind me here is a sideways model, full scale, of our machine. Everything inside of this kind of blue line right here, it's a little hard to see. Everything in here would be in the vacuum. This would be in vacuum region here. And everything outside is at ambient temperature and pressure. Inside of here where the plasma is, where the center of this egg-looking thing is, that would be the hottest and highest density plasma. That's where the fusion reactions would occur. We put in a deuterium gas, break it down into deuterium plasma, and then we heat it up to 100 million degrees or more. And we'll talk about the heating systems that we use. We'll talk about the way that we do this so that you get an idea of what it is that plasma research and fusion research is going on in the world. Now, the cool thing about this, as we walk out there in a few minutes and take a look at it, you'll see our machine as a big mechanical engineering nightmare. Wonderful thing, okay? It's a wonderful thing. And you'll see mechanical engineering. You'll see hard surfaces. You'll see things that are bolted together. But it's really a physics experiment. It's really a physics experiment. We've got 100 or so scientists working on this machine, 100 plus, working on this machine to find different aspects to make the fusion process ultimately easier and better. This is a short pulse machine. That is, we only have a high temperature plasma for about 5 seconds, but we do that 20 or 30 times a day when we're actually operating. So today is a wonderful day. We're not operating. We can go see the machine pit. We can see a few of the other areas in the background there. Now, I'd like to show you a little model of a three-dimensional model of our machine. And I can actually hold it up here, I think would be probably better. So here we see this cross section, very similar to what is behind me. We have the vacuum valve here. All of these yellow things represent magnetic coils. They either go, all of these yellow ones go around it this way, around the toroidal angle of the machine. And these big gray ones, like the big copper one behind me, these go in a poloidal direction. But as we run current through there, you know the right-hand rule, the magnetic field for this one actually goes into the vacuum vessel there. So we have magnetic fields externally applied magnetic fields. The plasma itself, the plasma is of the order 1.5 million amps of plasma. 1.5 million amps. And so when it becomes a plasma and starts rotating, it too produces a magnetic field. Now, magnetic fields are vectors, and so all of these things add up. And so we have to have a control system that's smart enough to change the currents in the coils that we have in order to make the plasma shape that we want and make the plasma density. We'll talk about how we control that plasma a little bit later when we go into the control room. Now, throughout this, I want you to ask questions. Even right now, if you like, what is that thing? What is that thing? What is that thing? And when we go out to the machine hall, please ask questions as well. I know you'll be looking at things that you haven't seen before. Now, for students that were getting their PhDs maybe back in the 1980s, we have a real tokamak that we got from school up the road, UCLA or USC. And this is very experimental in looks. It has the toroidal shape. This is on on its side. And this entire thing, it does not have a vacuum chamber per se here, but it would actually sit inside of a big vacuum chamber. The big vacuum chamber would go over the top of it. And so people could understand how to run, run the magnetic fields in here and confine plasma inside of here. So it's looks like it was quite a bit of work to be put together, but that's what we have graduate students for. And it worked out quite well, I'm sure. We got that given to us from the great folks up the road there. Okay, are there any questions right now? So what we'd like to do, yes.
Rick, can I interrupt for a second? I just got done with the other activity and I've been jumping to the 2 tracks to just say hello to everybody.
Congratulations on your video.
Thank you. Yes, it was interesting. But thanks everybody for joining. Diedrich, thank you so much for all the help that you provided. And thanks everybody for being here. I hope you all are enjoying the kits and the awesome presentation that Rick, the tour of D3 that Rick is giving you. Throughout today and next Saturday, please feel free to if you see me, send me a message, send me an email, and I will get back to you if you have any questions or any comments. But again, thanks so much for coming to the Teachers Day.
Thank you, Arturo.
Rick, take it away.
Okay, thank you.
Thanks, Rick.
And actually, okay. Rick, we have a question that came in on the chat.
Okay, well, I can't quite see the chat, so just go ahead and ask. I can hear.
Excellent. It says, how much energy do you put in versus how much energy are you able to get out?
Okay, we put in a whole lot of energy. At present, we get out very, very little. So this machine is not designed to break even or to actually produce any usable electrical energy. We measure the amount of energy that comes out by the number of neutrons that are produced in here. In a fusion reaction, we have light elements. Deuterium comes together, ultimately produces helium and a neutron. Produces a few other things as well. But the neutron is evidence of the fusion reaction. So as far as putting in, we put in millions and millions of joules of energy throughout the magnetic field, all the different coils in here, and we get out, as far as the neutrons are concerned, very, very little, down to just a few joules, let's say. Maybe a few kilojoules equivalent. So we put in a lot of power, we get out very little. But this is not designed for this. This machine was actually made in about 1986. So many of the parts are that old, but many of the external parts, the peripheral parts, the things that we'll see, the diagnostics and other cool things, are relatively new. They may be only a few years old, or they may be only 15 years old. This is a very active machine in the sense that we keep building onto it, keep building onto it, keep building onto it. So I hope that answers your question. Many, many megawatts in for power. Just a few kilowatts come out, and we don't use it because this is not designed to actually make any useful energy. All right, are we ready to start our little tour? Let's go. All right, so briefly, here's the size and shape of earlier tokamak. This was 1968 to 1969. You see the small volume. You see the small volume here, but you also notice that it was something that General Atomics had started, and it showed that we could have a few milliseconds of maybe 1 million degree plasma. So 1968, 69 is when we started working in the business, and we've been doing it ever since. And as we do that, our machines get larger. Here was the early 1970s, got larger. And then another machine that's not shown here would have been even larger. And then our fourth generation is that D3D that you see over there. So you see the size has gotten much, much greater. The volume of plasma is much greater. And we can do a whole lot more with it as far as heating is concerned and as far as diagnostics is concerned. All right, so follow me. And if we don't trip, then we will go into the machine hall. So we're going to walk down this little hallway here. You got it? We're going to walk down this hallway here, which is one of several hallways that we have to enter the machine hall. And we're going to open up a radiation shield door. It's kind of dark down here. Let's see what happens. We have radiation shielding around here. Bring that on over here and open that up. So you can begin to see a lot of stuff there. We're going to walk on in there and we're going to see what all that stuff is.
So Rick, we just had a question that said, will this be available for teachers to share with students? And I just want to address that. Yes, it certainly will. We are recording this. And so at the end of these 2 weeks, we will gather all these videos together and make them available to you via the Google Docs. Great question.
Yes, so again, this is the first time we've done this from a video
we need these 2 videos especially for our students, please.
Okay.
If you can chop that part for our students, it will be really good. We want to share that with our students.
Okay. Now I'm going to go ahead and take off my hard hat because the headphone is not working with that, and that's okay. I'll be careful not to bump my head. Normally this is a definite hard hat area, but we'll go ahead and turn this off for now. So you can see kind of the layout. It's a little bit difficult to see the actual tokamak. We have a better view for you in just a moment. And we'll certainly do a walk around here. We'll look at more things in more careful feel. Think we can switch? So we're going to switch cameras here. Are you okay?
Rick, we can't hear you. You're muted. Rick, you're muted.
Thank you.
There
Sorry
you
about
go.
that. Thank you. So we're going to open up a Nagy window if we can open that. Okay, here, just put it in here. Let's just plug this in. We're gonna go no video for a moment.
Thank you for the heads up. We're standing by.
It doesn't see that.
We see you again.
There we go. Let's take a look at this. There we go. There's a bird's eye view of the machine hall, and I'm going to walk over to where you can see me. So you can see the scale of this thing. Okay, can you see me?
Yes, we can.
All right, so here we are in the D3D pit. Now it's, I don't know, 50 by 50 around 70 by 70, and then it actually is a pit. There's 3 floors here, and we'll actually walk down to middle floor and we'll walk down to the base floor as long as our Wi-Fi connection holds up well. But behind me is the tokamak. Although it's very difficult to see, you can't quite see the pumpkin shape of the toroidal field coils, and that's because there's so much peripheral equipment around here. But it's very similar to when you open up the hood of your car, you swear there's an engine in there, but you don't really see the engine, you see all the peripheral parts. So the tokamak is in here, believe it or not. It's packed down behind there. And what I have over here on the right of me, for instance, are some heating systems, some neutral beam heating systems we'll talk about. We have a lot of diagnostics in here. The diagnostics that we use, we want to know what's happening in this plasma. That's the whole idea. This is research. So we can't come out here and touch it. We come out here and look at it. We can't come out here and taste it or hear it. So we have diagnostics that are all around here. We have cameras that look at the an actual image that comes out, and those cameras might be visible or infrared. We have detectors that detect magnetic fields, electric fields. We have detectors that detect radiation, such as neutrons that come out and gamma rays that are out here. We have lots and lots of diagnostics. This is the most diagnosed plasma, we think, in the world. So we have more than 70 or 80 very sophisticated diagnostics. The cool thing about that is that the diagnostics work on basic science principles that you're already probably teaching in your class. They work on principles such as diffraction, such as interference, such as electric field or magnetic field understanding. They work on nuclear particle detection, which maybe you have a little Geiger counter in your classroom. They work on lots of things that you're already probably talking about. So it's very cool that the science behind all this is already in your classroom. Now, we can look at stuff here. I know that from your point of view, it just looks like a mess in the garage, right? But nevertheless, behind me is the pumpkin-shaped tokamak with a lot of peripheral equipment around here. If there's anything here, anything shiny that you want to ask about, then feel free to let me know. I'm going to head on back over here. And we're going to continue with our
Excellent. We see the cameras are switched. Friendly reminder,
Okay.
Feel free to put a question in the chat or just unmute yourself and yell out, guys.
Yeah, just go ahead and ask.
I just have to say, hey, Alex, I hadn't seen you. Thanks for helping out, Alex.
That's Arturo saying hello. All right. Okay, so we're going to take a bit of a walk around. Feel free to ask if you see something or if you think of something as I bring up these comments about how we measure or how we heat things up. Let us know. Let us know. We're happy to let you feel free to guide us in our tour here. Remember, this is for you. So please, when you can, think about it and ask, what is that? What is that? Or how do you do this? How do you do that?
So Dietrich is asking about that black and red thing. Is that a belt?
Okay, so this black and red, thing right along here is a set of cryogenic lines, liquid helium, liquid nitrogen type lines that are on a flexible belt. Because this whole monstrosity here, all the way back to here, all the way back here, can actually be lifted up. It can be lifted up to be, instead of a horizontal angle, it can be lifted up to be at a relatively high angle. This is one of our neutral beams. When we get around to the other side of the machine, we'll see one that is lifted up. We're the only tokamak in the world that can do this. And the reason we do this is because the physics is different when we inject these high energy beams into different parts of the plasma. And you can't just steer these beams anywhere you want to. These are large 1.5 megawatt beams, about yay big, beams of energetic deuterium atoms and molecules. And they are the things that go in and collide with the plasma, give up their kinetic energy, and raise the temperature of the plasma to 100 million degrees. Without these neutral beams, we have what we call simply an ohmic plasma that sits around 25 or 30 million degrees, and no fusion happens for us. In order to have fusion to happen, think of this. It's kind of like a chemical reaction. We need particles, we need energy, and we can't have too many energy losses. So we talk about energy in terms of kilo electron volts, but we also talk about it in terms of temperature. Density, we talk about it for the number of particles. We have a certain density in there of particles. It's not very much, but that's what we can do. We can get high temperature here, but we can't get real high density. And then we try our best to reduce the number of energy loss mechanisms in the plasma, and that's called energy confinement time. In the sun, the reason it can do fusion at such a low temperature, say 13 million degrees, is because it has very, very high density. And another thing, the fuel in the sun is simply hydrogen, simply hydrogen. The cross section for a fusion reaction to occur with hydrogen is very, very low. And so for our low densities here, we would not have enough reactions occurring to do any decent fusion reactions. So we use deuterium, right? It's just one neutron plus the proton in a hydrogen. Deuterium sounds pretty exotic, but it's not. One out of every 6,500 water molecules in your body, in the ocean, in the water you drink, is a deuterium atom. It's not radioactive. It's quite stable on the Earth here, and we just buy it. We just buy a bottle of it, maybe $1,000 from the gas company that brings us fuel. So deuterium is what we use for our fuel. Okay.
Hey, Rick, not to interrupt you, I have a couple quick questions while you're standing there. Someone asked, is that a belt?
Is what a belt?
No,
I think that track that's behind you.
That was what I asked. Yeah, I already asked it,
okay.
And he answered it.
Okay.
But
and then we have another one. Can you? Oh, yeah, I'm sorry. And there's another question.
So when you talk about right, you got it.
Yeah, advantages and disadvantages of using. We're using simply deuterium as our fuel. We end up with a little tritium as a byproduct. This machine is designed to understand the plasma, the characteristics of high temperature plasma. And we're not licensed to use tritium as a fuel. However, the deuterium and tritium interaction occurs at a much lower temperature. That is, the rate of deuterium-tritium fusion, you can get much higher rate for a given temperature. So that would be the fuel that would be used in a real-life energy-producing machine. So does that help? The disadvantage of using tritium is itself radioactive, and you have to account for all the little microcuries that you have coming into the machine and going out of the machine. Princeton has done this many years ago, and JET in England has done this many years ago, at least for a relatively short time, just to see that things would actually work. And they got quite a few megawatts, of the order 10, I think, or so megawatts, 12 megawatts out of fusion power, not electrical power, but fusion power. So that's a whole lot more than what we can get here with our deuterium plasma.
So I'll ask a question. I'll ask a question just to follow up that. So where you're standing, can you stand there when the machine is operational?
That's a very good question. We cannot be inside of this machine hall when the machine is operating. And the two main reasons is electrical hazards and radiological hazards. The amount of electrical current out here is hundreds of thousands of amps. If there was an issue, if there was a problem, and something got electrified, then we would be at risk. So we're not allowed to be out here because of electrical. But in addition, once we're out here, during our shots where we have plasma and we have the neutral beams going in, there's a heck of a big neutron flux that comes out, and that would be detrimental to us as well. So we're outside of here. We're behind very thick concrete and polyborated walls, and that reduces the neutron flux outside of here of hundreds of times. So we're safe on the outside. We would not be safe on the inside. And so that brings up a very good thing too. Everything here is automated. Everything here is automated. Everything you see, all the valves that we want to open and close, the systems we want to turn on and off, everything is controlled typically by a wire or fiber optic outside the machine hall. So we'll show you when we go in the control room, we go in this place called the annex, we'll show you that as well. Okay.
Thank you, Rick.
All right, thank you. All right, we're going to continue on, and we will.
So
walk
Rick,
around.
I just saw this question come in. What do you do with the byproducts?
Okay, the byproducts are typically simply helium, maybe some
Rick, you're
deuterium
cutting
gas
out. Maybe
left
you should
over.
you cut out just a little bit, Rick.
Okay, so the byproducts are typically helium. Can you hear me now?
Yes, thank you.
Okay. They're typically helium, maybe a little tritium, and leftover deuterium. And those we just evacuate out and we send it out to the atmosphere. We account for what we send out, but it's low enough to be able to send that out. So here's another view, kind of a side view of the machine. You can kind of see the toroidal field coils that go up and down here. This one you cannot see. You can see one over there. Those are the big coils that we run 127,000 amps of current through. There are actually some little coils you can't quite see, but they go sideways up here. And then we have all these diagnostics. These green boxes are plastic, borated plastic. Inside of here would be cameras. Now we use borated plastic as a neutron shield. So inside of here would be a camera, maybe the size of a loaf of bread. So we have all this shielding on it. So not only do we have neutron shielding here, but inside we have lead bricks because this machine also produces a lot of X-rays. And then inside of that, we would have copper sheets around the camera because this machine produces a lot of electromagnetic interference. So the best offense out here is a very good defense. We've learned that over the years. The detectors in these cameras can be very sensitive to neutrons, to X-rays, and they're very expensive cameras. Inside of here is a very expensive visible camera. Up top over there, there's one that's a very expensive infrared camera. And down below here is a very fast camera. I think 75,000 up to 75,000 frames per second. So we can see some very, very fast imagery of things. You see a lot
Rick,
of,
going back to the, I'm sorry, Rick, really quick, going back to the byproduct question, there's no carbon monoxide?
that is a good point. We have only deuterium in there. We don't have our atmosphere in there. We don't have oxygen. We don't have nitrogen. We don't have argon in there. We evacuate that, the vacuum chamber. We bring it down to 1/10 billionth of the pressure of the atmosphere, and then we introduce deuterium. So it becomes 99.99% deuterium inside of there. And there's no carbon dioxide, no carbon monoxide, no carbon emissions at all. The fusion energy, one of the advantages of fusion energy is that it does not produce greenhouse gases. Cool. All right, so let's walk on around. You're welcome. You see some more diagnostics here. There's a little microwave diagnostic system here that uses low power diagnostics. There's a lens here. Now, you and I are familiar with lenses in optics when we use this visible light. This is a lens that, if you looked at it, it would have the same shape, but it's actually made out of Teflon. The Teflon acts as a great lens for microwave. So we have to match the materials that we use with the wavelength of systems that we're looking at. So in this example, there's a large lens down here. You and I cannot see through it because visible light doesn't go through it, but microwaves go through just fine. All right, we're going to continue on around here. We're going to stand on top of this neutral beam system here. These neutral beam systems are systems that, go ahead and show down here. Behind this box right here, this is an iron box. Inside of here is a ion source. And what that does is it makes a small deuterium plasma, something about the size of half of your oven. Imagine your oven, about half of that. And it makes a small plasma in there. And then there are extraction grids that have electric fields, extraction grids inside of there. And it takes the positive ions that you've made in here and extracts it across 80,000 volts. Now, we can't have ions just zooming on down here because there's so many magnetic fields around from the machine. So right after these ions are extracted, they go through what's called a neutralizer. And that neutralizer is just some background gas in the volume. And those ions slam into a background gas atom, and background gas being deuterium molecules, B2, and steal an electron. And then they go on their merry way down here. So we can inject of the order 1.5 to 2 million watts of power this way, with these neutral beam injectors. They're very important and integral part of this fusion operation we have here. Now we're just walking around here. We won't necessarily stop at these unless you see something of interest. We do want to look at some waveguides that we put in 1 million watts each of microwave energy into the machine as well. So microwaves, very similar to what you have at home, but our gyrotrons, as we call them, produce about 1,000 times the amount of microwave power that your microwave at home does. And it's very difficult to see maybe, but these aluminum tubes, these are aluminum tubes, and we call them waveguides. These aluminum tubes come in from outside the machine, outside the machine hall. They're up, and outside. And we'll go back and see where they originate. And we bring 1 million watts of microwave power into here through these little waveguides. So not only do we have particle interactions, we have a lot of electromagnetic interactions as well. The smoke and mirrors that we use in our fusion research is all about electricity and magnetism and how those affect particles. So that's a very important thing that you can bring into your students when you're doing anything having to do with the electric fields. We're talking about capacitors or inductors. We have them out here in a very large manner.
Hey, Rick, we have a question. Do you use that heat energy?
Do we use what energy?
It says, do you use that heat energy?
So I'm not sure what you mean by heat energy. The microwave energy?
Yes.
Okay, so we use that microwave energy to make the plasma do some interesting things. It doesn't heat up quite like the neutral beams heat up the plasma, but we can do some other interesting things with those microwaves. They'll launch into some, they'll resonate with some parts of the plasma that they can heat up, or they can kind of fix if the plasma is kind of broken. So we can do some things with that microwave that you cannot do with the big old bulky neutral beams. It doesn't heat up quite like at home where you're exciting water bonds in your food, but it does interact through resonance with electrons that are gyrating in the plasma.
Thank you, Rick.
Okay, let's see if we can go downstairs. This is normally off limits to tours even when we are here. So here we are in the mid-level, and we'll walk around and take a look at one of those big neutral beams. You don't have to worry about this sign here, and it's hard to see, but it says, due to restricted overhead and uneven walking surface, the lower access pit is off limits to visitors. Pshaw. Today, everything's on limits. So let's walk around and see what one of these big neutral beams look like when it's up in the air. You see these wires and cables. This is how our information gets out of the machine hall and into a place that we can read it with computers. So here we are, mid-level, and look at that big old 70-ton neutral beam hanging up there. Now, Alex had a great deal of input on the engineering of this. A lot of new and novel things had to be put in here. You don't just lift these things up and leave them there. So it's a very remarkable engineering feat. It took us about a year to put that up. We had to take it out, had to pour more concrete down below, had to put stuff back in and modify it like crazy. So it's a very unique piece of engineering. And it makes us, again, a very good research laboratory for the world in terms of fusion research. All right, let's head downstairs. We're going to walk back the path we just came. And we're going to go downstairs even further. We'll pass up that nonsense sign that says off limits, phooey. Now again, this is a hard hat area, and if I were actually doing work out here, I'd have my hard hat on, but I will be careful. I don't have much to cushion if I bump into something up there. Okay, so now we are down at the very base level. This would be like the basement of your house. And above me, above you is the tokamak. Now, let me turn on a flashlight here. These are water lines. These are water lines that go up. And you can see that's the bottom end of the tokamak. Not real pretty. But these are lots and lots of hoses. We have to keep things at room temperature. That's what the hoses are for, to keep water running at room temperature. The tokamak is up there, and again, you can't quite see it, but it is up there. It's sitting on these giant pillars, these large stainless steel pillars. In the machine hall here, we use only stainless steel or aluminum. We don't use many things that are made of steel because they're all magnetic. So we have very large amounts of stainless steel and aluminum in here that we utilize for structure and for connecting things together. Let's come over here and look at some of this kind of Frankenstein bus work. I know when you're putting wires together in your house, you have some small wires. But here's some bus work, a little hard to see, but here's large pieces of copper. Now they are These copper pieces up here are uncovered, but these down here have some tape on them, like electrical tape, but we call it Kapton tape. And these bring in 120,000 amps of current from our power supplies that are outside of here. So you can see the big bolts, the big chunks of copper, lots of stuff down here. This is why we don't want to be in the machine hall when it's operating. We don't want to run across 120,000 amps. Now, to put that in perspective, your house gets only about 100 amps, maybe 200 amps. So we're using as many amps in one coil as 1,000 houses. Okay, let's see some other things we have down here. You can see the myriad of hoses, water hoses, and gas injectors, and all kinds of stuff down here. So these are gas injectors here. Think of it like on your automobile. You have little fuel injectors. Well, that's kind of what these are. They behave in a similar manner. So we can put in deuterium or whatever other gases we want. We've got lots of water here. So the engineering that goes into this, we have fluids engineers that work with water. They work with cryogens like liquid helium and liquid nitrogen. They work with vacuum. We consider vacuum a fluid because we're always pumping out at least a little bit of atmosphere in there. So it's a very complex device. And what you're seeing again here is mechanical engineering. But again, it's for a physics project, but really it's a social project, because if we get this right, then all of our progeny, all of our grandkids, great-grandkids will have a cleaner source of energy to use to when they're goofing around working on a computer. We have diagnostic systems down here. We have lasers that come in from the outside world and fire up through the machine. We'll talk a little bit about that later on, about scattering, how we do scattering, and just a whole lot of stuff down here. We have to be careful when we're working down here, and we have to be honest. If we step on something and break it, we have to go to the owner and say, hey, your thing is broken down there. You better fix it before you need it. So we're very conscientious about being open if we make a mistake down here. All right, we're going to head back up, and we'll head over to our cryogenic area and ECH, and then we'll go into the control room. I think we're doing fine on time. Feel free to ask questions.
Thank you. You're doing a great job, Rick. Really appreciate it. I don't see any questions in the chat right now.
Okay, good. Thank you. So we're going up 2 flights of stairs. So we were down in the lowest, down at the basement. You see all of our hard hats here that we use for when we're working in the pit. So now we're going to go back to an area, a couple areas here. We'll make a brief stop. Here's something that you're familiar with. Suppose you pull a cold, dry soda can out of the refrigerator on a humid day. What you end up with, of course, is condensation on the outside of that can. Well, we use that very concept inside the machine and inside the neutral beam to reduce the amount of excess gas that we have in there. So we use liquid helium, which is expensive, and we use liquid nitrogen in something called cryogenic pumps. So they're vacuum pumps. They're not high pressure pumps, and they just allow exposed, very, very cold surfaces to portions of the plasma. They're kind of hidden, that will condense atoms and molecules that we don't want in the plasma anymore. So we utilize this a lot. Liquid helium, you all know where we get helium from, right? We find all the
Rick, we
kids
just
that
had a quick, oh,
Yeah.
sorry, we just had a quick question. Can you elaborate on the use cases for aluminum and stainless steel also? So what type or types of stainless steel are you using?
Okay, so we primarily use stainless steel number 316. We also use 308. The aluminum that we use, 6061 is the alloy that we use. And again, we use that primarily because it's non-magnetic. And in a room with lots and lots of magnetic fields, if we have large pieces of magnetic material like standard steel, that can influence what the ultimate magnetic field will be inside the plasma. So we reduce that. So this is our cryogenic engineering pump here. So again, this would be like refrigerant in your refrigerator, but on a very, very, very large scale. This is our control room for the cryo. It's a bit messy right now. The guys have been working very hard. You can see a few dials and knobs. Gotta go this way. Okay, so now we're going to go back to our microwave generator area. These things are called gyrotrons. And like I said, they produce 1,000 times the amount of microwaves that your system at home does. So you can see up top, there's a lot of plumbing, a lot of pipes and wires, up there. Place is a real labyrinth of mechanical engineering, fluids control, power supplies, all kinds of things like that. What this gyrotron is. Now your microwave system at home, the actual little microwave generator of yours at home is about the size of your hand, and it'll produce a kilowatt of power. So that means that you can put your water in there for about a minute and it'll be hot enough for tea. Well, this is something called a gyrotron, and we'll talk about how it works here in a moment. And it produces 1,000,000 watts of power, 1,000 times more. So on paper, that means that if you were to put your cup of water in here, in 1,000th of a minute, it would be heated up to tea temperature. That's how much goes out there. Now let's just look briefly at how this works. Now, not shown on here, there would be a magnet down here. And the electrons are brought in from the bottom. They're accelerated up through a gyrate.
Rick, you're freezing and cutting out a little bit. The video's frozen.
Video's frozen.
Okay, now you're good. I can see you now. Now I can hear you.
Okay. Okay. The Wi-Fi is good. That's all right. And so this gyrotron, we put in electrons down below through a magnetic field. It's not shown here, but there's a magnetic field. The electrons gyrate. They give off electromagnetic energy. The electromagnetic energy comes up here. We use a set of mirrors to bring the electromagnetic energy out, the microwaves, but the electrons themselves continue on to the inside of this big collector. So the electrons are part of the electrical circuit, but we turn the energy of the energy given on by the accelerated electrons into microwaves, and we take those and we send them out to the machine hall. So this one has been here for many years. It makes for a good display. We might try the machine. Let's go back here. So now we're going to see where these gyrotrons live, the actual ones that are up and about. So here's our gyrotron vault, and some of them are not here, but there is one right here that we can look at. So right here, right here, along here is a magnet. The electrons come up from the bottom. They go through the magnetic field. They gyrate. The electrons themselves will get into that collector, that black collector up there. But the microwaves themselves will come out. They'll go through waveguides, such as this, and head out to the machine hall. So we saw them out in the machine hall. We saw them up on top going into the machine, and this is where they originate. So the concepts that are good here is electromagnetic radiation that's produced from accelerated charges, which is the only place we get electromagnetic radiation. And in this case, it's microwaves, very similar to what you have at home, but on a much larger scale. Lots of plumbing back here. All right, we're going to head back to the control room, and we'll talk more about plasma there. Now remember, this is a industrial scale research lab. So there are lots of things that are relatively new, and there are lots of things that are relatively old. Matter of fact, your grandfather probably had these kinds of cabinets when he or your grandmother were working. They still work. We're going to go through an area called the patch panel. I hope that we have Wi-Fi back there. Can you hear me okay?
Yes, we can, Rick. Thank you.
Okay, thank you. So back here, these are bars that are connected to the coils out of the machine, and we can put different power supplies onto these coils. So this is kind of like the a patch panel that you would have for telephones in the old days. We only have a limited number of power supplies, and yet we have 18 coils that we want to fire up. That is the controlling coils, the shaping coils. And so we can put the relatively small power supplies, connect them to each one of these. The big coils, like the B field coil, the big toroidal one, and the ohmic heating coil, which is a primary transformer, those have dedicated power supplies and they're always connected. But here we can make changes because changing here will allow us to make changes in the shape of the plasma. Very versatile. It looks low tech, but it's very versatile. So we're going to walk through what we call the
Rick, the video froze. We lost you for a second. Okay, you're back.
Okay. Yeah, we're back in the catacombs here. I don't know how well we'll do, but again, this is a forefront. Again, we've never done this before. So all of these big blue boxes are part of the power supply that provides 127,000 amps to our main toroidal field coil. Now, just to show you, that was an electrical engineering area, and that's kind of dusty and dirty. Let me see if I can get into one of our premier optics labs and show you how nice and clean. It's air conditioned, it's well lighted, except back there where the lights are off. This is a Thompson scattering lab. And we have 10 very high-powered lasers that we can fire into the machine. They scatter off, the light scatters off the electrons in the machine, and then we detect that scattered light. And from that, we can find out what the temperature and pressure is in the machine. So this is one way we can measure temperature and pressure in the plasma. Very sophisticated setup in here.
Hey, Rick, just a heads up, it is 10 a.m. Central Standard Time, so we do have another 30 minutes.
Well, that's quite a coincidence. We have another 30 minutes to show you.
Excellent.
Thank you, Julie. Thank you, timekeeper. We're heading back to the control room. Well, we're heading to the control room. We haven't been there yet. We'll talk more about plasma. We'll show you some homemade plasmas, maybe instill some inspiration that you can make as well, and talk about your plasma ball and what's in the plasma ball, and see how we, the little bit of computer savvy that we have. So we're coming back to where we started. We're going to pass that up and go into the control room. Hold on. So this is our control room. We have it a little darkened right now because we want to show plasma stuff in here. But we'll get over to where we can see some other things. And while I get something set up over here, Alex can show you a little bit more about what we do here. Let me set that down. And why don't you show them over there, and I can talk while we're doing this. So Alex is showing you some screens, and it's those screens that we look at pretty much in real time. A little hard to tell, but in real time about what we can understand what the plasma is doing. We can look at the plasma current. We can see power supply information here. These take the place of real-time oscilloscopes that we would have used 15 years ago. As a matter of fact, 35 years ago, when they were doing fusion research, they would have a bank of oscilloscopes up here, and then they take pictures with it with Polaroid cameras, and that was their data collection and analysis. They'd have to get out the ruler and measure the voltage and things on there, but that's the way they did it. And now, of course, with computers, lots of computers, we can do that much quicker. Now, independent of these, we can look on the screens of any of these computers that are in here, and there's probably 75 of them. And, well, there's 75 workstations. They're connected to computers outside of here, and you can connect to probably 15 different computers. So you have at your fingertips a wealth of data that you want to look at, either temperature or pressure, infrared imagery, all these different things that are right here for scientists to look at. So that's pretty cool. So I'm going to go ahead and walk on over here. I'm going to plug in this computer because it's getting a little bit low. And we're going to look at some plasma again. Let's see. Let me plug in this computer. So we talked a little bit, we saw a little bit earlier with the Tesla coil. Remember, we had this little Tesla coil, and we had a tube out there. And the tube is very similar to what you see in what we would call a neon light. Okay? Although this neon light is a little bit more sophisticated, in the sense that this particular one has argon in it, and it has this white coating. So it has a fluorescent coating in it. Fluorescent coating similar to your half-coated fluorescent tube. And your half-coated fluorescent tube you notice there's a standard little tube, except the Princeton folks were able to get the makers of this to actually do a special run and only coat half of these. You can't buy these. This was done on a very kind of personal basis, and it was done very nicely. And so you can see an empty tube here, or an uncoated tube, and then a coated tube down here. And if you look closely, you can see maybe, and I don't know if it'll show up here, I don't think it will, but there are tiny little drops of mercury in here. It's the mercury that does the trick in making a fluorescent light fluoresce. Remember, fluorescence simply means high energy to low energy. So what's happening here is we're exciting mercury atoms. They give off high energy ultraviolet light. That ultraviolet light hits the phosphors in this coating, and that gives off lower energy visible light, hence the name fluorescent light bulb. If I excite this with this, you can see the argon there, and you see that this coating is fluorescing on that side. And I can see, and maybe you can too, a little bit of mercury, tiny little mercury beads in there. This is why when you break these, you want to clean it up, and you don't want to throw them in the trash. Try to have these recycled. Now we'll show you how you can use that with your plasma ball as well. So can you turn that light off over there? So we're going to turn the overhead light off now so that we can actually look a little bit more. You have your plasma balls, something like this. It may look a little bit different. Now these are attention getters. These are definitely attention getters, in the sense that you have this on in your room. The kids are going to come by, when we have kids in the rooms, they're going to come by and play with this. There are lots of things that you can do with this. And at the end of each day, or maybe at the beginning, you should take some Windex or alcohol and clean off all the little kid smudges that are all over here. It's quite safe. Now, what kids will often do is they'll take they've shown this, they'll take a small coin, put it on top, and that small coin then collects charge. And let's see if this shows up. If you just lightly, is it showing up? If you just lightly,
I can see it. Hopefully others can. Yes,
okay,
that
it's
looks
just
great.
a tiny little spark there. And if you do that enough, the skin of your finger will have a little soot on it. But it's something that can be done. There's other things that you can put on aluminum tape on here as well and measure the amount of current that's on there. But you can also excite your half-coated fluorescent tube. We can put this on here, and it becomes excited there. And if you want, if you're good, it takes a little practice. I don't have room here. I'll see if let's set this down here. So what I'm going to do, we see that there's light here, out of here. And what you can do, if you're careful about it, put that there. And using your fingers around here, you can look like you're stuffing the light back into the globe. Or you can pull it out. Now, why is that? That's because you become part of the electrical circuit here. But it's a cool thing to show the kids, because they're going to go, huh? What? Pull the light out, whoops, and put the light back in. Pretty awesome. Or you can just lay this across. Now realize that this uncoated portion is giving off some fluorescent light. So you wouldn't want to have, I think you may have a wrapping on yours or a plastic tube. So try to keep that in place, because there is a little bit of fluorescent light coming off here. I mean, ultraviolet light coming off of here. Okay, let's move on to more plasma and see how plasma can be affected by magnetic fields. Many years ago, Alex put together this tube this tube. It's just an empty tube normally. Let's see if we can bring the, no, this has got to go down. So we're going to change the camera angle a little bit here so that you can see our pancake plasma. Okay, so lift that up a little bit. Okay, so here's a plasma. It's just a tube. Down in the bottom there, we have a neon transformer, neon light transformer. You can pick those up for about $40. And it's high voltage, 5 kV, so it's kind of dangerous. You have to be careful. But you can get a hold of those, and you can make this. Inside of here, we have one electrode sticking up from the bottom, one electrode down from the top, and the top electrode is being fed by some high voltage wire here, a very thick wire with another plastic tube on it to make sure it's insulated well. And so that's plasma. But now let's see how we can affect the plasma with a magnet. So I have a magnet here, okay, and I'm going to put this up against the side at the base on the right-hand side, and you can see that I can affect that plasma. That's our whole bread and butter here, that we use with magnets, not permanent magnets, but electromagnets, and be able to move these back and forth, be able to control the plasma. So if you and your students made something like this, now it also requires a vacuum pump, and the vacuum pump is a, I don't remember how much that was, 120, 250 now. That is you can probably get them at different places. Okay, let's turn the light back on, and we'll take a look at a taken apart plasma ball. So originally this plasma ball was together. Get in focus there. And we took this apart so we can show you the parts of the plasma ball. This is taken apart. Down below here is a little high voltage source inside, a little circuit that produces high voltage. There's a little insulated wire that becomes uninsulated, non-insulated up on top here. And it produces the high voltage needed to produce the arcs and striations in the real plasma ball. Now the plasma ball itself is a blown glass system. It has a input here. It's not really an input. It's still part of. I can put my finger in here, but the tube that you see on the inside is really part of the inside of the vacuum chamber. And up inside of there, you can see that there's a little bit of looks like stainless steel steel wool in there, which is what it is. And when you put all those together, this is has some gas in it, neon, maybe a few other gases in it. Then one can have an actual plasma ball. So your little plasma ball is a high voltage source, kind of like a Tesla coil. If for some reason you break this and you have this exposed, this can be very dangerous if it's turned on and plugged in. So if for some reason you do break your globe, unless you want to use this for other experiments, then I would just go ahead and put this away where the kids can't get to it. Now, there's one more thing we want to show you, and I'm going to show it in video form, but I want to talk about it. Here is a little, it looks like a big light bulb. It looks like a light bulb like this, but it's not quite a light bulb. Inside of here, inside of this one, is a source of electrons back here that heats up a filament. The electrons get pushed out, and then we can manipulate them with magnetic fields. It's difficult to get a good image of this, but we did get one earlier on a video, and I want to show you that. And what we're going to do is show you that with a permanent magnet that I'm going to bring around from the back and from the front and the light. But I'll need to switch to a video. So bear with me for a moment. Let's see if I can work this out. Okay, that's not what I wanted. I had it on top here. Are there any questions so far?
Excellent timing, Rick. There is. This came in earlier. I didn't want to interrupt you, though. They're asking what kind of license do you need to work in the control room? Who issues the license?
So it's not so much how much of a license that we need in the control room, because we just get hired and we work here. But there is a lot of training that we go through. We go through a lot of training with safety. They don't hire us unless we know something about electricity and magnetism and about these other things. So as far as General Atomics may have a license to operate the whole system, since it has electrical and radiation. Let's see, we're trying to get here. Can you still hear me? Julie, can you hear me?
Yes, sorry, I was muted myself. Yes, we can still hear you, and we thought switching over to the movie. Yep.
Yes. Okay, so we're going to see this movie. It's about the this cool little electron beam, and this is a standard thing that's used in physics classes. And let's just see.
If there's sound, we cannot hear it, Rick.
Okay. Okay. There is sound, but let's see.
I know when we tested it the other day, I could hear it. I just couldn't hear it just now.
Well, let me try something here. Does that work?
I do not hear sound.
Okay, here, hold on. We'll make it work. Don't worry.
Thank you for your patience, everyone.
Oh, that's interesting. Sorry about that. Okay, so I'll just talk through it. So we're gonna have the I'll just talk through it.
Okay.
So we're showing that side view, and we're going to turn the lights off here. I'm picking up a magnet, and we're going to go ahead and so the lights are off to the right. There you can see the filament is getting heated up. We'll see a blue line. Look at that. Isn't that cool? There's a blue line. Now, those are electrons there. Now, we cannot see the electrons, of course. So the manufacturer has put in some helium gas inside of there. And as those electrons go through the helium gas, they excite the helium gas, and that gives off light. So what we're seeing as far as the light's concerned is the helium light. Now, I'm going to take a magnet from the back side and move it along. And you'll see it bending. These are moving charged particles. Moving charged particles can be affected by a magnetic field. If I change the polarity of the magnet around, you see it goes the other way. North and south, different effects. Right-hand rule, V cross B. I can bring it in and make all kinds of cool shapes. You see a reflection in the back of the light. Make little pigtails. But this gives you an idea on how, if we were smart enough, we can produce a magnetic field or a combination of many magnetic fields to control our plasma. This happens to be just an electron beam. Our plasma would look much larger and would look a little different, but the concept of magnetic field affecting moving charged particles is what we're trying to show here. Okay. All right, so I see 1021 here. So we've talked a little bit about plasma, ionized gas. Cool thing about this, what Alex calls his tube over here, is the aurora borealis in a tube, because this is an air plasma in here. So where can you get kids interested in plasma? You can talk about magnetic fields. You can talk about the Earth having a magnetic field. And when sun particles come, positive and negative ions get trapped in the Earth's atmosphere. They move back and forth through our magnetic field. And if they collide with atoms up in the atmosphere, they'll produce light like this. So the aurora borealis and the aurora australis are end products of the plasma from the sun coming out here. And so that's a pretty cool thing. And the magnetic field that we have here, that we showed with the with this little device here, that's very important, because those same particles that come out from the sun, if the Earth did not have a magnetic field, those particles are so energetic that they just simply blow away the atmosphere. They blow away the atmosphere, and that would be a challenge for us, right? The oceans would then boil, nothing to keep the vapor pressure of the water down there. They'd boil away, and that would get blown away, and we'd end up with a very dry, uninhabitable place, very similar to Mars. Mars lost its magnetic field a very long time ago. And so as a consequence, it can't keep an atmosphere, and it can't keep liquid water like we can here on Earth. So magnetic fields and charged particles, plasma, can be found in lots of places, in stars, in plasma balls in your room, in the aurora borealis, or the effects of that. So are there any other questions? Okay, well,
I don't see any questions in the chat right now, Rick. Oh, sorry.
Tour of our D3D facility. I know it was something you were not anticipating, but we thought this would be a great chance to do it. We've never done that before. If we were in Memphis, we couldn't do that. And we could kind of show you some videos of it, but it's not quite the same as actually walking around here. So mechanical engineering, plasma physics, electrical engineering, computer science, we use all of those things. And of course, at the business level, we often have people like Julie Harris, who have backgrounds in non-technical, but they go out and they help spread the word about fusion and other products maybe that we're making. So with that, I guess we bid you farewell, and we hope you enjoyed this, and hopefully you find it interesting and you can use something about it with the teacher, with your students. Feel free to email me, rick.lee@gat.com, if you want further answers on something. Thank you.
Thank you so much, Rick. We really appreciate it. Feel free to ask him some questions. We have a couple minutes yet. Throw them in the chat, or go ahead and unmute yourself.
Hear you, Julie.
Can you hear me now?
Yes, I'm sorry. I had things muted here.
That's okay. No, that's okay. We have a couple thank yous in the chat. Like I said, we have a couple minutes left if you have some questions. If not, you guys can take a quick break. We'll start with our new session in about 10 to 15 minutes. I really enjoyed the tour. Just like Rick said, it's the first time we've got to do this. So thank you for your patience with us. I think it was a great first time, and this is recorded, so we'll make sure you guys have access to that recording at the end of all these sessions.
I have a question.
Yes.
Yeah, I was wondering, you mentioned that this has sterilization effects earlier. Is that true? Or have you found out, I mean, have you found any incidences where there may have been situations where like maybe there might be a thermophile or something like that that could survive in this type of environment? I'm just
Well,
wondering.
so early on, even 100 years ago, the doctors made little plasma devices, not quite this strong, but they would use that for disinfecting skin. They would try that to disinfect skin. Certainly, if you can interrupt cells and maybe actually rip open the cells of bacteria, then you can sterilize it there. Now, as far as large-term sterilization using this, I'm not aware of that. One can use radiation, gamma rays or X-rays to sterilize things, but I'm not so sure about the plasma part.
Okay, thank you.